Hello and welcome to today's webinar, which is sponsored by Trilion. I'm Matt Reynolds, editor of Packaging World magazine, and I'll be your moderator. Industry 4.0 is changing the landscape of R&D labs, quality labs, and manufacturing by ramping up efficiency and elevating quality to the highest of standards. With the evolution of technology, becoming an Industry 4.0 lab can be done in a few short weeks, saving your team time and money while providing more accurate data. In this webinar, we'll discover the top trends in testing that every packaging group should have on their radar. Before I introduce today's speakers, I want to let our audience members know that the webinar will be available for archive viewing at packagingworld.com within 48 hours of today's presentation. You'll receive notification when it's ready, and the slides will be available for download as well. Feel free to ask any questions at any time during the webinar by typing them into the questions pane of the GoToWebinar control panel. We'll take some time at the end of the presentation to address as many questions as time allows. With us today is Jack Irwin, Senior Technical Account Manager at Trilion Quality Systems, and he's been there since 2017. He supports both industry and university customers with non-contact measurement solutions, and says he's proud to support Aramis optical strain gauge technology in order to help users truly understand their materials and structures. And we also have John Moore, Industrial CT Application Engineer with Gom Americas, Inc. John is focused on bringing computed tomography solutions to quality labs throughout North America. With that, Jack, why don't we dive right in?
Thank you, Matt. Well, welcome everyone. As Matt mentioned, today we're here to speak about the top trends in testing that every packaging group should know and have on their radar, specifically as it pertains to next generation non-contact measurements. So, as you mentioned, our speakers today, myself, Jack Irwin, I work with Trilion Quality Systems. I support direct applications using a variety of Gom optical measurement solutions. I'm also an industry expert in packaging materials and structures. You see one of our systems in the bottom left of the screen. Accompanying me today is John Moore from Gom Americas. He directly supports computed tomography applications using the Metrotom 6 Scout for both interior and exterior metrology. And you have an example of one of his systems in the bottom right of the screen. Just to give you a bit of background, both Trilion and Gom America support Gom in North America. We support their product line. So Gom develops the software, machines, and systems for both industrial and automated 3D coordinate measuring technologies and 3D testing. I'm here today specifically on the Trilion side to speak about the Aramis optical strain measurement system. It uses a technique called digital image correlation for full field strain and deformation measurements. And it's also capable of dynamic photogrammetry, meaning that it's able to dynamically track point components. In addition to the Aramis system, there's also the Argus optical forming analysis system that's used very often in the stamping and tool and die industry for quality control. It replaces a process called circle grid analysis. We also have the Tri-Top system, which is an optical coordinate measuring machine used very often in the civil engineering and aerospace engineering fields in order to perform static measurements of generally large structures. Essentially, you'll use it to create a point constellation of a given area of interest and use it to perform static measurements to understand deformations over time or after a force has been applied. Another system that we're here today to talk about is the Metrotom 6 Scout, which is essentially a 3D X-ray scanner. Now, you might be familiar with a CT scan in a medical context, as in, oh, I broke my arm, I'm going to the hospital, I had a CT scan performed. But what the Metrotom 6 Scout is a CT machine that was developed specifically for metrology applications. And for that reason, it is the most accurate CT machine in the world as far as both interior and exterior product dimensioning. More on that soon. And finally, we have the ATOS full field 3D scanner, and that's exactly what it sounds like. It uses the same optical metrology technology in order to perform exterior measurements with millions of points of accuracy, and it's used very often for reverse engineering or rapid prototyping applications. Now, all of these systems work very well together. They operate within the same ecosystem, and you'll be able to use some of the outputs from these systems in conjunction with other Gom equipment. Let's start with Aramis optical strain for non-contact full field 3D deformation analysis. And again, we have one of our Aramis systems in the bottom right of the screen. Now, those of you on the testing world will be generally familiar with some of the instruments that Aramis replaces. You'll have your single point mechanical sensors and solutions For displacements, you might be using LVDTs or extensometers. Vibrations, you'd be using accelerometers, maybe a laser vibrometer. Finally, for strains, strain gauges, strain gauge rosettes. Now, these are all great tools if they're used effectively, but the problem is that many of them are just single points of analysis. And unfortunately, a lot of them are contact solutions as well. What's more is they're quite tedious to apply. If you put down a sensor and it becomes misplaced or fails during the test, you're going to need to retest. But if you use these solutions effectively, their outputs go on to validate finite element models, or FEA. You might be familiar with some of the softwares out there like LS-DYNA, ANSYS, Abacus, and these are all great simulation techniques. And FEA as a whole is a great technique in order to perform analysis on your specimens and perform great simulations. But it is just that, it's limited in a simulation sense. So what the Aramis system is really a great marriage of the two because you're collecting full field non-contact measurements. And here's an example measurement in the center of the page. And right off the bat, you'll notice that those measurements look very similar to a finite element model. It is very similar, and it allows you to pick up on local areas of strain concentration or deformation concentrations over the course of the test, and allows you to more intuitively interact with those models in order to refine them and adjust their boundary conditions. And by the way, we're doing so at a level equal to or better the standard testing solutions that exist. So let's talk about how that works. We have a 2-camera setup, as you see on the left side, and what we're doing is we're tracking the 3D coordinates of a fiducial marker, right? And those markers come in 2 forms. Either a single point, this is just a sticker, a black sticker with a white center that we apply to any area of interest that we want to track. And with that, we can perform this dynamic point tracking, as you're seeing on this prosthesis example. In addition to that, we can apply a pattern. As you see here, it looks a whole lot like TV static from a broken channel. It's a white base coat of white spray paint, and then we'll speckle on a black speckled pattern in order to have a completely randomized pattern on the object of interest. And that gives us hundreds, thousands, or even tens of thousands of data points that we can track over the course of the test or in order to collect full field results. So why does that matter? The fact that it's non-contact, it accelerates your testing as to where you don't need to apply physical sensors. The full field will give you insight rather than just getting one quantitative data point. You're seeing the entire data field very intuitively to pick up on concentrations that you weren't necessarily expecting. Most of our engineers are interested in strain or displacements, but we're not limited just to that. We're also capable of other measurements such as accelerations, velocities, rotations, what have you. But the cool thing is you'll measure once and you're capable of performing all of these measurements from the same data set. And we do that from a variety of different scales, everything from very small, think sub-millimeter size test, all the way to very large. We're testing things as large as military helicopters being dropped from hundreds of feet in the air. And it doesn't really matter what the material is. If we're able to optically track it and view the pattern over the course of the test, we're going to be able to measure. And we do that from a variety of speeds, from static tests to quasi-static, very low strain rates, to dynamic tests that get into the millions of frames per second. What's useful here is that the camera system allows for motion compensation, makes it insensitive to rigid movement between the camera system and then the object of interest itself. We can really understand the local deformations and not be influenced by gross movement. And the fact is, it's designed to adapt to your evolving needs. You're going to be able to apply the system from a very slow speed, simple test like a tensile test, all the way up to a very high speed dynamic test like a shock impact. You're going to be able to do this because the software is all the same. It's all image based. We just need the correct hardware to suit the need. And no matter what type of test you're performing, you're going to be able to validate your numerical simulations, your FEA, with this full field data and do it in a very effective and timely manner. So without further ado, these are some of the measurements that we've performed in the past. We have everything from a simple tensile test to shear test to more complex geometries like aircraft panels and rivets. The military helicopter that I had mentioned in an earlier example, but on this page, you're seeing several examples of different geometries and different strain signatures that the Aramis system is able to pick up on because it's tracking it optically. At a base level, we perform material tests using the Aramis system. We have an example of that here with the Aramis system on the left side and your MTS or Enstron load frame here on the right. And what we're doing is we're pulling a sample in tension and tracking the strain behavior over the course of the test. So we see all the colors changing on the sample to the right side as it's being pulled. And those are unique strain concentrations that are propagating throughout the specimen until it finally yields. This is actually a metal sample. And so what we might be anticipating in this case is Luther's bands that are propagating throughout the specimen until it finally fails. This sort of output is only a possibility with the Aramis system. You'll be able to pick up on those strain signatures throughout the sample, whereas a simple strain gauge would have a very hard time reading that. What's more is that we can take things a step further. When you're performing your basic material test, we can run tests according to ISO or ASTM standards in order to ascertain the material properties or understand the stress strain curves of the materials that you're working with in order to verify performance or optimize the materials that you use in your packaging products. Let's move on to some actual component tests on packaging products. We have one here. It's a bit of an older example from our colleagues in Germany. We have a laundry detergent bottle that's being crushed in compression. So right off the bat, a couple of cool things to show. On the top left side, you can see that we're directly importing our load. Kraft is force in English. And so what we're able to do is understand the product's deformations relative to the force that's being applied. In addition to that, we have a black line that's going on right along the center right here. That gives us a profile of whatever measurement that we're interested in this case, deformations. And so we're able to get a nice understanding of the profile measurement over the entire length of the bottle. And then finally, we have our color map, which is quite intuitive to understand. You're going to be able to understand, based on the color, the level of deformation that the product is undergoing. And again, this is tens or hundreds or even thousands of data points that we're tracking at any given iteration. A more recent, more fun example is this Gatorade bottle that we had applied our pattern to. This is just your off-the-shelf Gatorade bottle that you can buy at any Walmart or convenience store. And what we're doing in this case is I'm crushing it with my hand, and we're using our optical sensor in order to be able to track the strain over the course of the bottle. So go ahead and play it. So as my hand is contracting, we can see that the strain signatures will be picking up. We get a nice qualitative view of what's happening based on the color scheme that you see lighting up, but also we're able to put individual sensors anywhere that we like over the course of the bottle. So it allows us to essentially put down virtual strain gauges anywhere we're interested in. And by the way, we can do that before the test happens or after it finishes in post-processing. So we never need to retest. Let's take a look at a live example where we go through the software's workflow on a cantilever structure.
So to demonstrate the software, what we're going to be doing today is working with this cantilevered structure. I'm going to go ahead and scroll through the images here. What this is doing is we're actually deforming the structure at the back, and we're cycling this back and forth. Now, based on the pattern, that speckle pattern that was applied with spray paint onto this part, we're able to have the software discern several thousand data points. As a matter of fact, we're over 5,800 data points that we're able to see here. So a really dense data set, and there's a lot that we can pull from. To make this data set even more interesting, what we might do is import a CAD model. Now the CAD model is obviously interesting to us because it's a coordinate system in which we've modeled in. And so it helps to have our experimental data line up with the computer models. So we have that imported here. Of course, it's not aligned at this point. I'm going to go ahead and do that. The alignment process is very simple as far as it all goes. What we're going to do is perform an initial alignment, and we're going to be selecting 3 different points. 3 on the CAD file, and then 3 on the series of images that we collected. And what we're trying to do here is just get in the ballpark, so to speak. Looks like we're pretty good there. To ensure that we are, what we can do at this point is perform a local best fit. That's essentially telling the software, okay, well, here's your ballpark. Go ahead and finish the job for me within a given tolerance. So it looks like we're in really good shape here. Go ahead and select OK. And now we're in a coordinate system that makes sense with what we've modeled. As a matter of fact, if I'm interested in seeing that, I can do that. See it in the origin. Looks good. Go ahead and put that in the back. Now from here, we can make some measurements that are useful to us. We have the correct coordinate system, so let's check out some directional measurements. X seems to be particularly interesting in this case, so let's select it. And all 5,800 plus data points are already computed. We're just asking the software to see it, right? So as I scroll through these images, I can see the resultant strains on the structure as it's being cycled. A nice qualitative view there, but what I can do in addition to that is put down individual sensors. You can think of them like virtual strain gauges all throughout the surface of your specimen. And so with that, of those 5,800 data points, we have 3 that we're very easily able to track. And of course, I can pick anywhere on this surface component in order to be able to see that. I could flip this on its head entirely. I can ask for a brand new measurement. If we're using traditional methods, you might have to retest. In this case, we can pull from the same data set in order to see new information. So again, I can put down individual sensors, briefly recalculate the project, and see the resultant strains, this time in a new direction. Very useful information here. We have obviously an overview, but we can have those values plotted out all throughout the course of the test, all across time, and we can export these as a CSV file. Alternatively, what we can do, if we're at a stopping point, so to speak, and we found the information that we're really interested in, we can create a report page right within the software. A report page is a nice overview of the measurement of interest and allows us to convey the information quickly and effectively. So I'll go ahead and create that. I'll briefly create that for all of the stages of the project. And then from there, we'll be able to interact with it a little bit more of a PowerPoint style. Let's check out that report.
It may interest you to know that this software is available to you in an easy and direct way through the software called Gom Correlate. Gom Correlate is an easily accessible free software that's available to anyone online, where you'll be able to perform tests just like you've seen today and understand your product's deformations. If you're interested in applying a technique such as this in your day-to-day applications and ending the process with strain gauges or extensometers or some of the other nuisance products that are out there, we'd be glad to speak with you in order to understand a configuration that would best suit your needs. But for now, I'm going to be passing things off to my colleague, John Moore, who'll be talking about the computed tomography aspect of Gom's product line. So John, I will pass things off to you.
All right, thank you very much, Jack. So my name is John Moore. I'm an employee for Gom Americas. We have an office here in Charlotte, North Carolina to support our regional distributors such as Trilion. So I am the local CT expert, if you will, working with this Metrotom 6 Scout you see here. And yeah, let's dive right into it. So what we're going to see here is a representation of the inside of the CT machine. So typically with any computer tomography, you're going to have an X-ray source, the scanning object, and the detector. And similar to what Jack said, you may have heard of this in a medical field where an X-ray source spins around a human body. We're using the same principle here, just spinning the part instead of it being a human body, for example. And so your final output of any CT scan is going to be an STL model like this, which is a very high resolution and highly accurate digital twin of whatever you want to scan. And so this is a plastic part here, for example. And the nice thing about Gom is we are experts in metrology. So what you're seeing here is a heat map or a color map, if you will, kind of showing the deviations of the part from the CAD model. And you can measure all kinds of things in this software, GD&T, outer dimensions, inner dimensions, pretty much anything you can think of. Now we'll get into that a little bit later. So here's just a testament to the resolution of scan that you're going to get from a Metrotom 6 Scout. So this is a small plastic piece coming from one of our Gom branded pins. This is probably 1/2 inch in length. And what you're seeing here is very high resolution digital twin from this small piece. Anything you're seeing on the surface is going to be actual surface quality. It's not any type of residual noise or anything like that. So yeah, we just really like to show this piece to kind of exemplify the resolution that you can get out of this machine. And furthermore, looking at this piece, you have these small scratches here from where the piece was cut. And this is a little surface defect map we put on it to kind of show the kind of precision we're looking at. So this is a 1.2 micron divot here, or depression. And just for reference, human hair is around 60 to 70 microns, and we're looking at a 1.2 micron scratch on the surface here, which is pretty impressive. Kind of revisiting computer tomography and its origins. So first CT kind of came out in the 1970s for medical purposes, as I mentioned earlier. Then industrial CT was finally produced for material analysis. And the more people start to learn about CT and its capabilities, the more it starts to penetrate the quality control market and being able to understand what's happening on the inside of your part as well as the outside. So some of the nice features of computed tomography in an industrial setting. So it is a non-destructive and a non-contact way to do quality control on any of your parts. So you can see whatever's going on the inside without cutting it in half. Obviously, it is a highly accurate and very quick method to measure any of your parts that may work in our machine. So like I said earlier, it is going to create a digital replica of a part. And so this is just a deodorant can here. We scan the lid and you can see all the nicks and crannies on the inside, do any kind of geometrical measurements that you may want to do on the inside, which is a very strong solution. So you can do any kind of geometric fitting elements on the internal pieces of a scan that you do. So with our inspection software, you can put in all of the tolerances and anything being read out on the drawing for you to inspect. In addition, so by the nature of the technology, you are going to be able to see everything on the inside of your pieces or your parts being measured. And in our brand new 2020 software, we now have void analysis and porosity analysis, which is an incredibly strong solution for a lot of our customers, being able to pinpoint where there may be voids on the internals of a piece or part, or for example, a crack that may be running through a ceramic part, or all kinds of things. In addition, the nature of the technology allows us to do material segmentation. So as you see this bottle cap here, there are two different types of plastic. So the material or the machine can see the two materials separately and do an assembly analysis on these pieces. It's important to also mention that our Metrotom 6 Scout system is a metrology CT. And what I mean when I say that is you can actually quantify the measurements that you're taking, rather than previously a lot of our competitors or things that were in the market prior to what we're working with today. Was just qualitative analysis, just looking for cracks and voids that may be on the internal of a part, but now we can actually quantify these things to a very high degree of accuracy. Just some of the facts and figures. So we do have a 225 kilovolt source, which is middle of the line. This can measure any plastic, pretty much any aluminum, and it can get up to some stainless steels and nickels and titaniums, just depending on your application and the size of the part. Just for the sake of time here, we'll skip through a few of these. So accuracy, it is plus or minus 3 microns throughout the measuring volume, plus length over 100 according to our VDI tests. So if we take a look here, this is actually another model of the inside of our Metrotom 6 Scout. Basically, this can give you an idea of which parts will fit inside your CT. When we look at voxel sizes, you see here, this is basically a 3D pixel, so this is equivalent to your resolution. Long story short, we work with the principle of magnification to increase resolution. But this part that we're looking at here, for example, you can get the best resolution at a 27 micron voxel size. But if you can sacrifice resolution, you can do batch scanning in the larger measuring volumes and get up to, I've seen anywhere from 5 parts all the way up to 300 small parts being measured at once. So whenever you look at this economy of scale, you can get scan times down to 3 seconds per part, which is incredible in a high throughput situation. Another nice feature that is included with our Metrotom 6 Scout, we are pretty much the only ones on the market that have an XY axis on our rotation table. So this allows for an automatic part centering operation to take place when you're scanning, as you see here. So pretty much with any other machine, you're going to have to do this operation manually, which can take 30 minutes to an hour in some cases, having to power up the machine, then turn the machine off and do manual movements in this case. So right here, this is just a quick look at how our software is set up to operate this machine. So we are pretty unique in the way that we are a one software solution with our CT system. So we can do acquisition, reconstruction, inspection, and reporting all in one software, which is incredible for the ease of use of the machine. You could teach somebody to use this piece of equipment in about half of a work day, I'd say, in my own experience at least. So you'll see here a live view of whatever you're scanning. So this is a small electrical connector. What you're going to see here first, we've already powered up the machine. What it's doing now is the auto centering operation. So this is pretty much one of the only parts you have to interact with manually. You have to draw this green box around your part wherever it may be in your measuring area. And then once you hit OK, it automatically pulls your part to the center of the detector, which allows for a higher resolution from being in the perfect center of the detector. And like I mentioned earlier, it's a much faster workflow as far as industrial CT goes. And so from here, I think we're going to hop over to a quick inspection tutorial, and we'll be right back. So now that everybody has a good idea of the acquisition side of our CT technology, I'd like to take a look at the inspection side, or the back end of the technology, once you have a completed STL. So what you're looking at here is an iced coffee bottle that we scan here in Charlotte before promptly sending it up to Jack in Philadelphia, who crushed this with his Aramis system. I think we'll take a look at those results a little bit later. But just to give you an idea of kind of the resolution we're looking at here, this is the mesh structure of a final STL coming out of the CT machine. So what you're going to see is this polygon pattern, if you will, that's kind of giving you an idea of what the resolution is looking like in this piece. So if we look at the general information, you'll see that there's generally 1.5 million points on this piece, which is pretty data dense, obviously, and all these points are highly accurate and repeatable down to about plus or minus 3 microns. So pretty impressive stuff there, but I just want to, for the sake of time, just kind of walk through some tag scenes that I put together here regarding this bottle and just kind of give you an idea of what's possible within our software. So I think one of the most powerful pieces of inspection work that we can do on these plastic bottles would be material thickness. So you're getting the outside and the inside of the bottle, which allows you to obviously take a look at this type of inspection. So you'll see right off the bat here, you're looking at kind of the ribs and being able to see how thick these ribs are compared to just the normal outer surface. To go one step further, we can take a look at the sink marks that are outside of these ribs and get a good idea. It looks like they're about 50 microns roughly deep. So this can kind of give you a good idea of what type of deformation you're looking at with these ribs. In addition to that, we have a parting line analysis here. So what we do is create a cylinder around the entire body of the piece and then do a bit of a deviation color plot. So it gives you an idea that, okay, your parting line is roughly about 68 microns higher than the outer surface, which may or may not pass given your specifications. So it is a pretty nice little feature that you can look at here and do some analysis in this way. Additionally, we can create 2D cross sections off of this STL. So you'll see here already, you can kind of get a good look that you're having a material thickness that's much higher down here. What you'll see up here is a caliper. So this is an outside edge caliper giving you the entirety of the bottle length. Another nice way that you can inspect is looking at this or these threads here, which allow you to kind of get an idea of the interaction between the cap and the main body. And there's quite some advanced inspections you can do on things like that, but I don't think we have time for that here today. To move on with the section analysis, you can also do a multi-section analysis, which allows you to export these cross sections as an elements file. So this allows you to do some reverse engineering tasks with this type of data, which is super powerful for some of our customers. They really appreciate this feature. There is a lot of stuff that you can do with this type of data. Moving on to a different piece. So this is actually a, I don't know what you'd call it, maybe a plunger, detergent dispenser plunger, if you will. So you just push this rubber piece on the back and you can pour out your detergent into your load of laundry. So a nice thing about this is that, for example, this black piece here is a rubber plunger mechanism and everything else is plastic, so you can actually differentiate between these two materials and do inspection on each individually, even though they were all in the same scan. So this is kind of the nature of the technology, being able to pick up different densities in this way. As well, there's also a lot of detail on the interior that you would never be able to see otherwise. Being able to see how these two things interact with each other and how it's built internally, and being able to do very precise measurements. This is a pretty cool little scan we did here. And then finally, so with a lot of plastics, you're going to have voids and things like this. So what you'll see here is actually some void analysis that we've done in this software. And this is literally a 2 or 3 click process to be able to look at this type of thing. So let me make this a little less transparent so you guys can get an idea. So this is actually a cap off of that same detergent bottle. So you'll see, yeah, you can measure your detergent out. But there are these very tiny voids towards the rim of the piece itself. And you'll see it's also color mapped out here like we've seen earlier. So according to your legend and some deviation labels here, you can actually see the volume of each little void. And you can do inspections in this way. So you can also add tolerancing to this type of inspection and be able to, kick the part out or kick the inspection out if any one of your voids is too big or something like that. So that's just an introduction to kind of what we can do in the software with the CT data. I hope you enjoyed looking at this data, and feel free to reach out to me with any of the contact information that you've seen in the presentation earlier. I'd love to talk to you guys about it a little more in depth and give you guys a better idea of what all we can do with this technology.
Well, thank you, John. That was pretty insightful. So from the CT scan that John just performed, we're actually able to bridge the gap into some of our other technology straight away. We took the CT scan and imported that into the Aramis testing software for some further analysis. So you see that right here. The software has a really nice reporting feature. So what we're able to do is show you some cool insights that we've already collected on this. I'm going to go ahead and switch to it right now. So again, this is the CAD model. Pretty interesting to point out. millions of data points that we're tracking here, but we can see some really cool geometry. There's a dent in this the top rung here of this bottle, probably because of some grocery store maneuvering or something along those lines. In addition to that, we apply a surface component to this, and we did that very similarly to some of the other projects that you've seen. We'll apply the base coat of white paint and speckle on the black paint. And with that pattern that we've applied, we're able to track over 21,000 data points over the course of this test. So really insightful data. You see, all those intersections that you see on the right side of the screen. Those are all individual data points that we can track. And again, you can think of those as individual virtual strain gauges or displacement sensors. And so we have a whole lot of data to pull from and potentially validate those finite element models for the packaging products. And here's our first test. We have a compressive test taking place here. So we can see that this bottle is being crushed. The geometry reacts very similarly to what we'd expect. So this the cap is being pushed in, and we can see that folding in on itself until the bottom finally yields right at the end of the test there. Similarly to all the other projects that we've seen, we have the full field color map, which gives us an idea of the magnitude of the deformation as it's happening. In addition to that, we have individual sensors spread all throughout. Another cool aspect on display here is the fact that we're able to incorporate the load directly. You can see that in the top left of the screen. And what that allows you to do is to make your measurements relative to the load. And that connection is very simple. We just have a BNC connection to an analog channel on our load frame, and we're able to import that load directly. Another cool impact or test that we're seeing on display here is going to be a deviation label that's tracking strains, the principal strains on this bottle as it's being crushed. So if you remember the last slide, we were seeing that that bottle was folding in on itself. We're able to see on that lip where the geometry changes to understand the strain behavior until it finally yields. And the same could be said on the minor strain side. So these are going to be really the compressive strains as they're taking place until the bottle folds in on itself and it yields, so about -5% there at the end. And then finally, a really cool integration between the data sets. On the left side, we have the material thickness map that was brought to us by the CT scan that John performed. A couple really cool features that we're seeing here. Just like the Aramis measurements, the colors designate the different magnitudes of material thickness throughout the entire bottle. We see in the center of the bottle, for instance, that the material is thicker and there's some product defects in place, whereas in the top of the bottle as well as the bottom are a bit thinner material-wise. And wouldn't you know it, if you look over on the right side, you can see that the deformation patterns seem to be in line with that material thickness change, as to where the center of the bottle was stronger, was a bit more resilient, and the bottom of the bottle and the top of the bottle were a little bit more flexible and failed more quickly because they were made up of a thinner material.
All right. Thanks, Jack. That brings us to the end of the presentation portion and to a few questions that we have had waiting for you. The first one asks, with this CT machine, are there any possibilities to automate the workflow?
So yeah, great question. Basically, within the software that we typically utilize, there is two things you can take a look at. There's a scripting mechanism that automatically can script your workflow to where you just have to, click play every time you want to measure something, and it'll go all the way from scanning to inspection. And in addition to that, as I mentioned earlier, there's a batch scanning mechanism where you can scan up to 300 pieces at once. And all of these pieces can automatically be put into their own stage in our software and inspected individually and have a report output, if you will, pass or fail for each piece. So that is a pretty impressive feature that we do offer.
Okay, good. Another question, perhaps more on the blocking and tackling. How do you fixture the parts you wish to scan?
Yeah, that's also a great question. So we're typically working with plastics all the way up to metals. So unlike a lot of other scanning solutions where you might have to pay, $10,000 to $20,000 for one fixture to be manufactured, you can literally manufacture your own fixtures with any kind of foam, insulation foam, plain model foam, and just some hot glue. As long as you fixture it within the middle of the measuring volume, it may take you 5-10 minutes and a couple dollars of foam, and you can do this on your own. So yeah,
Okay.
great question.
Good. Another audience member asks that, or mentions that the speckle pattern looks difficult and asks how hard it is.
So I can field that one. The speckle pattern is actually not difficult at all. It really is just a base coat of white spray paint, and then we'll speckle on a black speckle pattern there, and that's done with your Home Depot garden variety spray paint. There's not a whole lot of variety that goes along with it. You'll have a coarser pattern for larger objects and then a more fine pattern for smaller objects, but that's really all there is. The software is pretty intuitive as far as it goes with figuring out how to interpret and read that pattern. So it's nothing to be scared of at all. It's quite easy to apply.
Okay, thanks. So what coordinate system does your sensor use?
Well, that's a great question. The coordinate system that the system natively uses is that of the camera system. But what we're able to do within the software, as you saw demonstrated, we're able to adjust that as we need to. We can perform an alignment as to where we can set the coordinate system manually, or we could align it to a CAD coordinate system so that we're performing measurements in the same coordinate system that we're modeling in, which is something that's generally very useful.
Okay, and can you also see temperature?
What's great about Aramis is the fact that you can incorporate temperature information from thermocouples or infrared cameras directly into the Aramis measurement. This allows you to understand thermal strains, for instance, and isolate thermally induced strains, for instance, as opposed to mechanically induced strains. So seeing temperature overlaid is definitely a possibility.
Okay. Another question asks, how do you handle motion in your cameras?
Well, a really good question there. And within the software, there is a feature called a rigid body motion compensation. So essentially within the software, I'm able to determine a specific point that I'm interested in or a specific reference and make that rigid within the software. And then all subsequent measurements would be based off of that rigid body, right? So it allows us to make relative measurements and allows us to make measurements that are useful to us.
How fast can you record?
Well, there's really no limit as far as it goes. We're really more tied to the camera hardware that's out there. There are camera systems that get into the millions of frames per second. The software, there's not really a limitation as far as that goes. We're just waiting for the cameras to catch up.
All right, another question that came in asks, are there two different softwares when CT scanning? I noticed you moved from a CT software to an inspection software.
Yeah, great question. So what we saw early on was the Gom CT professional software, which is for acquisition and inspection. And then the tutorial I did towards the end was our Gom Inspect software, which is just the bare bones inspection that you can do within the STL and CAD file. But this is incorporated in a Gom CT professional license. So all this is bundled up into one software.
Okay, and another question here asks, does the material need to be homogeneous?
So on the Aramis side, absolutely not. We work with some pretty complex composite materials or different collections of different materials that don't necessarily have much to do with each other. What matters for us and our purposes is if we're able to apply a pattern to the object that we're interested in, and if we're able to optically track it. So if we can see it, we can measure it.
Okay.
And so I can answer this one on my side as well for the CT side. We've had a few customers that come to us with, plastic injection molding parts, and we'll see little specks here and there within this within the part. And it turns out you can actually pick up these different little specks of metal that may have come from a manufacturing floor, and you can actually quantify, what percentage of the piece has these defects in it as well, which is a pretty cool feature from the CT.
It is. Another question asks, what's your range of specimen or structure sizes?
Well, on the Aramis side, what I can mention is there's not really that much of a constrained range. We've done tests that are sub-millimeter in size, even some tests even smaller than that with scanning electron microscopes, all the way up to very large. We've done a series of tests on military helicopters, even been involved with some structural testing on the James Webb Space Telescope, for instance. And so there's really not a limit to it. And what we can do on our side, if there's a specific application, we can speak with you and configure a system that would fit best with what you're looking to accomplish.
Good. And another question that came in asks about the calibration process.
All right, so at least for the CT machine, we do have a self-calibration option. So we do ship all of our CTs with a macro and micro calibration object. And it's literally just a 2-click process. Any operator can do it just by putting these artifacts within the machine. So it's not like, we have to have anybody from Gom or Trilion come out to calibrate your machine every couple months. You can do it weekly if you want to, which we actually do recommend.
Good. Well, that brings us near the end of our time here. So thanks to both you, Jack and John. That also brings us to the conclusion of the webinar. If anyone in our audience would like to learn more about anything that either John or Jack discussed, you can see on the screen in front of you right now, there's their emails, contact information. So we really hope that you found the topic informative. I certainly did, and we appreciate everyone for joining us today. So we will see you next time.